Happy snow day, AP Calcers. It's not nice outside, but this is AP Calc and we just keep going. No matter wind, snow, rain, hail, whatever, we keep trudging on. So, today, you guys can get started on the Unit 5 test. And then in class tomorrow, we can go over any questions on the Unit 5 test. On Monday, as long as Monday's a C day, then we will do the Unit 5 AP review, and then Tuesday you'll take the Unit 5 AP test. So that's what we got. But I don't know what for sure will happen the next couple days. So, hey, we got to get going on this so we get this done. So here we go. We're given in the first problem here that the first derivative is this of a function. We want to know where the function is increasing, okay? So if the first derivative is positive, then it's increasing. If it's negative, it's decreasing. So we take the first derivative and let's make just a little line graph here and figure out where it's increasing, decreasing. So there are some critical numbers going on. If we set this equals 0, we get a critical number of 2. The denominator has an asymptote, so that acts like a critical number. So 2 and 0 are our important numbers. And if you look down here, everything's 0 or 2. So that gives you a little idea what's going on. All right, so if we try the number 3 in this function, put a 3 in for x. 3 minus 2 is a positive number, so you have positive over positive, it's going to be positive over here. So it's definitely increasing on this side of 2. If we put a 1 in here, we get a negative, because the third power keeps it negative, over positive, so it's negative at 1. If we put in a negative 1 here, we get a negative over a negative, which is a positive. So it's increasing from negative infinity to 0, and from 2 to infinity. So the answer is A. So when the first derivative is positive, the function's increasing. We found where it's positive, found where it's increasing. All right, what's the absolute maximum of this function? Well, to find the absolute maximum, take the first derivative of the function. So the first derivative is negative 12x to the third plus 24x squared plus 36x. If we factor out a negative 12x out of here, we get x squared minus 2x minus 3. Set it equal to 0, so x equals 0, and then factor these two, x minus 3, x plus 1. So x equals 3 and x equals negative 1. Okay, so we know all those numbers. If we plug those numbers into the original function, at x equals 0, we get 0. At x equals negative 1, if we stick negative 1 in here, we get negative 3 minus 8 plus 18. So that would be like 7. If we stick in 3, we get 3. We get negative 3 times 3 raised to the 4th plus 8 times 3 raised to the 3rd plus 18 times 3 squared equals 135. There we go. That's the absolute maximum. Because these are extrema. So, yeah, minimum, local, max, probably there. So it probably goes like something like that. upside down w. So there we go. All right. The second derivative function is this. Which interval is it concave up? Well, it's concave up where this function's positive. Now, it's kind of hard to tell where this function's positive. So if we take our graphing calculator, clear, we can find it pretty quickly. And it says right here, use a graphing calculator. So we're going to use it. So I go e to the x squared, slide over, minus the sine of x. And if we graph it, where is it concave up? Well, does it ever cross here? The answer is no. It's always positive. So if it's always positive, it's going to be all real numbers. Okay? If the second derivative is always positive, it's all real numbers. All right, twice differentiable function. What can we say about the graph -6, -1? Well, the value at -6 is -1. At -6, its slope is 0, so that means it's a minimum or a maximum at -6. At -6, the second derivative is -3, so that means it's concave down. If it's concave down, it looks like that. So because we know this is 0, we know that is a maximum point. Okay, so where's the point of inflection? Well, that's where it changes concavity, okay? It looks, and this is kind of hard, it looks like it changes concavity probably just right there. It's concave down, and then it changes to concave up. I think C would be the only change in concavity there. I don't think it's B, because it still looks like it's going downward through there. But then it starts to go upward. An upward bowl, downward bowl. So I think C is the only one. Where's the absolute minimum of this function? You have absolute minimums where the first derivative is equal to 0. So you set 9x squared equal to 0. And so x must equal 0. So you say, well, it has to occur at 0 or at the ends of the interval. So you're going to check -2, you're going to check 0, and then you're going to check 2. And just plug them into the original function. So -2 to the third is -8. -8 times 3 is -24. Why did I even go to the calculator for that? -24 plus 8 is -16. So this is -16. If we stick in a 0, we're going to get 8. If we stick in a 2, we're going to get 24 plus 8, which is like 32. There's our absolute minimum, -16. Does this function have critical points? We'll have to find out. What's the first derivative of it? Well, the first derivative of it would be 3x squared plus 8 over 2 times the square root of x cubed plus 8x. Okay, how do we get that? Well, it's 1/2, because this is x cubed plus 8x to the 1/2 power, so it's 1/2 times that to the -1/2, which is that, and then times the first derivative of the inside, which is that. So if we set that equals 0, multiply the bottom by 0, that just cancels that out. So 3x squared plus 8 equals 0. So 3x squared equals -8. I mean, you're not going to have any critical points because it won't work out. Okay? Because x squared cannot equal a negative number. Okay? So can't take square root of a negative number, no critical points. All right, justification why this point is a relative minimum? Well, the first derivative goes from being negative to positive. The first derivative is negative, that's the slope is negative. Then if the first derivative is positive, then the slope is positive. So that would be a minimum there. So because it crosses from below to above, that's why it's a minimum. Okay? Looking at these graphs, what's a derivative of what? All right, so let's start with this one. Okay? Its slope is positive all the way until right there, which is -4. So it should be above the axis till -4. It's above the axis till -4, and then it continues above the axis. Well, here the slope is negative. It should go below the axis. So this isn't the original function. So let's go to this one. See if that's the original function. We're a negative slope to -4, and then a positive slope after there. So it's negative until -4 and positive after. So this would be the first derivative of this function. So let's see if this is the second derivative over here, where slope is negative first, then it's positive from like -5 to -3, positive from like -5 to -3, then negative after that again. Yep, this looks like the second derivative because it's a derivative of this. So it would go 2, 3, 1. 2, 3, 1 is choice C. Looking at this function, okay, looks like a cosine curve. Let's multiply by 2. Select the intervals where the first derivative is positive, so slope is increasing, and the second derivative is negative, concave down. So increasing slope, concave down. Changes concavity there and there. Concave down, increasing slope from there to there. Looks like that's a winner from -2 to 0. Okay. All right. What's the justification that we have an inflection point at C? Well, where it crosses the x-axis, okay, when it crosses the x-axis, there's a change in concavity. So it would be A. This aquarium holds 32 cubic feet of water. What's minimum possible exterior surface area? Okay, so volume for this, you have a base, and a height. So it's base squared height. Surface area for this thing is you have the area of the base, which is base squared, and there's 4 sides, which is 4BH. Okay, so what we want to do is use this volume, 32 equals B squared H, solve it for H, so 32 over B squared is equal to H, and then for this H, plug in 32 over B squared. So if we plug that in, then we take the first derivative of this. But before we take the first derivative, let's simplify it. 4 times 32 is 128, so we get 128 over B. So the first derivative of the surface area is 2B, and then this would be minus 128 over B squared. Set that equal to 0. Move that over, so 2B equals 128 over B squared. Multiply by B squared. 2B cubed equals 128. B cubed equals 64. So B must equal 4. Oops. B must equal 4 because the cube root of 64 is 4. So this is 4. This is 4. 4 times 4 is 16. So the height must be 2. Okay? The height has to be 2 because our volume is b squared times h, which is 32. Okay, that's the only way I make 32. So what's our surface area? Well, it's b squared, which is 16 plus 4 times 4 times 2. So this is 32, this is 16, so it's 48 square feet. All right, there we go. This one I already answered. Can you use the mean value theorem to say this equation has a solution between 2 and 4? So we know the first derivative is this, okay? So we find the average value, which is f of b minus f of a all over b minus a. F of b would be 1/4. F of a would be 1/2 over 4 minus 2. So the numerator is negative 1/4. The denominator is 2. So that's negative 1/8. So the first derivative is supposed to be equal to negative 1/4. But this is equal to negative 1/8. You can't set negative 1/4 to be equal to negative 1/8. So no, that is why it does not work. Where do we have points of inflection? Well, that's where the second derivative is equal to 0. So the first derivative of this function is 2 negative, there's a negative sign there, negative 2x cubed minus 18x squared minus 54x. The second derivative of this function is negative 6x squared minus 36x minus 54. All right, if we factor out a negative 6, we get x squared plus 6x plus 9. Set it equals 0. We get x plus 3 quantity squared equals 0. So x equals negative 3. So at negative 3, we should have a point of inflection. It is a double root. So let's check this. Just to graph it, graph the original function just to see if it looks like negative 3 is a point of inflection. Come on, turn on. Y equals. Clear out what's there. Here we go. Negative 1/2 x raised to the 4th. Forgot my x. X raised to the 4th power minus 6x raised to the 3rd power minus 27x squared. Graph it. Ooh, we can't see what's going on. What's going on is things are happening too far down. So let's change the window. Let's go from like negative 6 to negative 1. And let's make the y minimum 100 and see if we can see what's going on down there. Still too hard to see what's going on down there. Let's change the window to negative 500. So you can see it's kind of concave down, and then it's probably going to change to concave up right here somewhere in between 0 and 3. Because if we change our window a little bit more, let's go to like, instead of negative 1, let's go to like 4. See, it's concave down, then, ooh, kind of looks like all concave down there. Since we have a double root here, that could like change on what's going on, whether we have a point of inflection or not, okay? Because I know it equals 0 here, but since it's a double root, since it occurs twice there, this might not have a point of inflection. Let me make sure I put in the right equation. Negative 1/2 x to the fourth minus 6x cubed minus 27x squared. Yeah, that's the right equation. So that's why we double check. I would say it had no points of inflection. Okay, even though it looks like -3 would be a point of inflection. Okay, where is this function concave down? Well, here. Point of inflection, we can test this again, and I kind of screwed up the page now. Go back up. There we go. Another way to check this is to check on either side of -3. So let's check -4 into the second derivative, and let's check -2 into that second derivative. If we put -4 into the second derivative, we get -2 times -4 raised to the third power minus 18 times -4 raised to the second power minus 54 times -4. Enter. That's a positive 56. And then if we put in -2, we're just going to take that same equation, highlight it, hit enter, and change my 4s to 2s. That's a positive 52. Okay? So, as we can see, it's positive and positive. It doesn't change concavity because this is the same for both. So, no inflection points. All right, which intervals is this function right here, concave down? All right, so we could find the second derivative. So the first derivative, well, let's do this. Let's try the chain rule once. The first derivative will be 2 times x plus 3 to the negative second times 1. And the second derivative, the second derivative would be -4 times x plus 3 to the negative third. Okay, so where is it concave down? Where is this negative? Well, it's negative where the bottom is positive. Okay, where is the bottom positive? Well, when x is bigger than 3. Okay, because otherwise it'll make it negative. So where it's bigger than 3, -3 I mean, is here. If we want to check it, and I know the last time I checked it, it didn't work out so well. Kind of got a wrong answer. Well, no, I got a right answer. -2 divided by parentheses x plus 3. There's the original function. If we graph it, let's go zoom 6 back to our 10 by 10 window. It's concave down here from -3 on. Okay, we're almost done here. Where does this function have a relative minimum? Well, that's where the first derivative is equal to 0. 3x squared minus 4x minus 4 equals 0. So let's do the quadratic formula really quick, because I don't know how to factor it just in my head right now. I guess I could, but let's do the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So it's 4 plus or minus the square root of 16 plus 48, which is 64 over 6. So it's 4 plus or minus 8 over 6. So it's 12 over 6, which is 2, or negative 4 over 6, which is negative 2/3. So it's either 2 or negative 2/3, these two. Where does it have a relative minimum? We could stick them into the function, or you could just cheat, go on the graphing calculator. So at 2, there's a relative minimum. At negative 2/3 right here, it's a relative maximum. Okay, so 2 would be a relative minimum. Okay. So let's do the mean value theorem. So f of 2 minus f of negative 4 over 2 minus a negative 4. So if we put in a 2 here, we get 8 minus 32, which is negative 24. If we put in a negative 4 here, we get negative 64 plus 64, which is 0, over 6, which is negative 4. Okay? That's the first derivative of it. So we set the first, or that's what this is equal to. So then we set the first derivative equal to this. So we go 3x squared minus 16 equals negative 4. So 3x squared equals negative 16 plus 4 is negative 4 plus 16 is 12. Divided by 3. X squared equals 4. X equals plus or minus 2. So it has to be a negative 2 because that's within the interval. Can't be an endpoint. Okay, last one. Write an equation so the horizontal line that is tangent to the curve is above the x-axis. So it's a horizontal line. So we know it has to be part of this function, 3x squared plus y to the 4th plus 6x equals 253. We know that the numerator must be equal to 0 because it's a horizontal line. So negative 6 times x plus 1 has to be equal to 0. We know the denominator, 4y cubed, cannot be equal to 0. Okay, and if it's above the x-axis, x must be, y must be greater than 0 because it's going to be a y answer. So we take the first derivative and find that x equals negative 1 to make 0 there. So if we stick x equals negative 1 into this function, we get 3 plus 4y minus 6 equals 253. Oh, plus y to the 4th, not 4y. So y to the 4th minus 3 equals 253. Y to the 4th equals 256.